Welcome back to our fiber optic training. We're about to start part 2 of the training. For those of you who did not complete part 1, you can find a link to that video in the description below. The first video, like most of our videos, are approximately 15 minutes in length. So once you finish viewing that video, you can find the link back to this video in its description below as well. If you have not yet subscribed, this may be a good time to do so by clicking the subscribe button below, and also click the notification bell so that you'll know when new videos are released. Videos are released at least once per month. So that's it for housekeeping. Part 2 of the training starts on the next slide. We'll start the training off with a quick review of what was covered in part 1. In part 1, we covered the layers of a fiber optic cable, starting with the core, which is right in the middle. The cladding surrounds the core, then the buffer, and the jacket. As you remember, the core is pure silica glass, and so is the cladding, which is dosed slightly differently. And the buffer is protection for the core and the cladding. The jacket is the external layer, which you can see from the outside, like this yellow material here is the jacket of the fiber cable. We also talk about the fact that with a fiber optic cable, we use a light signal to send our information through the fiber optic cable. If you should compare a fiber optic cable with a copper wire, with a copper wire we send an electric current through the wire, which is used to carry our information through the wire to the other end. Now with the fiber optic cable, we use a light signal to carry our information through that fiber optic cable. Now as you can see here, you have a pattern of light going right through, and the reason this is because of the core and the cladding. The core is in the middle, the cladding is on the sides. The cladding is used to stop the light from exiting the fiber optic cable. Without this cladding here, in the blue area we have representing the cladding, without that, the light signal would just go right through and disappear, would never get to the other end. So the cladding is used to keep the light signal within the core of the fiber, which is referred to as total internal reflection. This is where the signal is kept into the fiber cable until it gets to the other end. Now this is the picture representing a fiber optic cable. This area here is the jacket, the outer layer of the cable. This area here, like copper, this gold area, this is part of the buffer. And so is these brown pipes here. These are also part of the buffer, and this material within the pipes is also part of the buffer. All of this is the buffer area, and the buffer, as you know, is made to protect the core and the cladding, which is right here. This is the core in the middle with the cladding surrounding it. Now all of this is the buffer, which protects the glass within the fiber cable. Without this material to strengthen the cable, the core and the cladding would be vulnerable to breakage and destruction without this. So the buffer is very important to protect the glass within the fiber cable. Now there are two types of fiber optic cables. We have single mode fiber and multimode fiber, and these two cables have their own unique purposes within the fiber optic industry. Now the single mode fiber is used primarily within the telecommunications industry. Now here we have the central office where telephone lines are residing and also internet lines. We're using the single mode fiber optic cable to get it out to the destination where it needs to get to, like a local area. And within that local area we have a splitter, and this splitter is what we use to get the signal to all the different customers at different addresses. Now we'll be talking much more about this subject as we get more into the fiber training, but I just want you to see here exactly what single mode fiber is used for. Now we have multimode fiber here as well. Now multimode fiber is used to connect businesses together. Here we use as an example a university campus where we have building A, B, and C. And in order to connect these buildings together, we're using a multimode fiber cable between these buildings. Now, there's a reason why we use multimode fiber for the university campus connections or for any business that want to connect buildings together. And there's a reason why we use single mode fiber for the telecommunications industry. And you would all get a full understanding of this as we go on and get deeper into the training. I just want you to have an understanding that there are two types of fiber optic cables: single mode and multi-mode. Single mode is used for the telecommunications industry, and multi-mode is used to connect buildings within a university campus or any building that needs to be connected together. First, we're going to talk about single mode fiber. Single mode fiber is also referred to as single mode step index fiber. It has a very narrow core between 5 to 10 microns. Microns is the measurement in which we measure the size of the core. Single mode fiber has one input signal, laser. This is the laser input signal here, and the reason we use laser is because the size of this core is so small. We need to transmit a very narrow beam of light through here. A larger beam wouldn't work. Like LED type light signals are larger signals. They take up more space, so they will not work for single mode fiber because it has such a small core. Now, the average size for single mode fiber cores is 9 microns in size. You can get between 5 and 10 microns, but the most popular one is 9 microns. How it gets that name, single mode step index fiber, is because the step design for the light signal going through the fiber optic cable. As you know, the reason this is when the light signal bounces against the cladding and reflect back in the core until it gets to the other end. Now, for multi-mode fiber, we're using LED type light signal. For the core of the multi-mode fiber cable, we have between 50 and 100 microns. This is much larger. Remember, single mode fiber was only between 5 to 10 microns. Multi-mode fiber is much larger than single mode, between 50 and 100 microns. So here we're sending an LED type signal, which is much larger, and it takes up much more space within the core than the laser. But because of the size of the core of the multi-mode fiber, we can actually send 3 of these signals through the core of the multi-mode fiber. And it also uses this step design to get from one end to another. Another thing I want to touch on here, you might have seen is 9/125, and you may be wondering here what this means. You also see 50/125 and 62.5/125. Now, these are all this is 9. This 9 represents the size of the core, as I said before. The 125 represents the size of the core and the cladding. Now, if you measure from this edge here, which is a cladding, right over to here, you'll get 125 microns. So this is 9/125 microns for single mode fiber. Multi-mode fiber would be 50/125 is the most popular multimode fiber cable. 9/125 is the most popular single mode fiber cable, but we also have 62.5/125, which is another size of multimode fiber. 62.5 would be the size of the core, and 125 would be the size of the cladding. So of course, this 125 measuring across here would include the core and the cladding altogether, but it's just referred to as the size of the cladding. Now we use a particular source of light, which is a particular wavelength at a certain frequency. Not every light source will be good for fiber optics, but I just want to take a look at all the different sources so that you'll have an idea of the different sources out there. Now here we have the light, the wavelength, and the frequencies. Gamma rays. Gamma rays kill cancer cells. Now the wavelength is 0.01 nanometers and the frequency is more than 30 EHz. Now X-rays is for the inside of the body, where you can view the inside of the body, and the wavelength is 0.01 to 10 nanometers. The frequency is between 30 EHz and 30 PHz. Now ultraviolet, this is observed by the skin, fluorescent lights. 10 nanometers to 400 nanometers is the wavelength, and the frequency is between 30 PHz and 790 THz. Now visible light, this is how we see. Without this frequency and wavelength, we would not be able to see. This is the frequency that we see in. The wavelength is between 400 nanometers and 700 nanometers, and the frequency is between 790 THz and 430 THz. Now next is infrared. This is what we use for fiber optics. This is the source of light that we use within fiber optics. Now the wavelength is between 700 nanometers and 1 millimeter, and the frequency is between 430 THz and 300 GHz, which is gigahertz. Now most of us will be familiar with gigahertz. Most of us are not familiar with these other very high frequencies because we very seldom use them. Gigahertz is more popular, along with megahertz and kilohertz and hertz, of course. Now if you want to go a bit further, we have microwaves for cooking and radar, etc. The wavelength is between 1 millimeter and 1 meter, and the frequency is between 300 gigahertz and 300 megahertz. Now radio stations and TV stations broadcast with a wavelength between 1 meter and 100,000 kilometers. And the frequencies is between 300 megahertz and 3 hertz. Now for radio stations and TV stations, they use mainly the frequency. You'll hear a radio station is broadcasting at a particular frequency on the band. But for fiber optics, we use the wavelength. So now whenever we're talking about fiber optics and the signal that is sent out through the fiber optics, we're going to be talking about the wavelength. We will never refer to it by the frequency. Infrared light source is what we use for fiber optics, which is between 700 nanometers and 1 millimeter. As I said in the last slide, the infrared light spectrum between 700 nanometers and 1 millimeter is what we use for fiber optics light signals. This doesn't mean that we could use just about any wavelength between 700 nanometers and 1 millimeter because of scattering and absorption. These are problem areas within the infrared light spectrum for fiber optics. And what we do, we pick wavelengths that have low incidence of scattering and absorption. First of all, we're going to start with scattering. We have a light signal going down the fiber optic cable, and we have some arrows drawn here. What this symbolizes is this light signal comes into contact with a molecule sitting within your fiber optic cable. Now, for those of you who aren't aware of what a molecule is, a molecule is two or more atoms combined together. And if you are not aware what an atom is the smallest component of any element. It has protons, electrons, and neutrons within there. Now, so it takes two or more atoms to make a molecule. So we have a molecule sitting here, and your light signal comes into contact with that molecule. Well, what happens when that occurs is that your light signal goes in all different directions. It scatters, and that's where the name scattering comes from. All of the signals that is scattered in other directions other than the intended path will be lost. So all of these signals here will be lost. This one here is the only one that would remain. So what happens here is that your signal is weakened considerably as a result of coming into contact with the molecule, which causes scattering. This is something that manufacturers strive to prevent. Another problem here is absorption. Absorption is when your light signal comes into a molecule, but in this particular case, what happens is that heat is created as a result of that. Your light signal is absorbed into heat. So all the signal that is absorbed into heat will not get to the other end. So this is another problem that weakens your light signal, preventing it from getting to the other end. Both scattering and absorption are undesirables within the fiber optic cable, and manufacturers strive to prevent them. Okay, here we're going to be talking about this graph here that displays scattering and absorption. We have a line here that shows scattering, a high incidence of scattering in this area here, and it goes through an absorption area here as well. Has a high incidence of absorption here, and as it goes down, the scattering gets lower. The incidence of scattering gets lower in this area, and also absorption in this area, of course, is lower than this area, but it's also absorption, which is an area to avoid, and the scattering in this area here is also very low. So in this area here, we start at 700 nanometers here at the end, but between 700 and 850 nanometers, manufacturers decide not to use this area to manufacture a signal generator sending any wavelengths between 700 and 850 nanometers, because the incidence of scattering is too high. So they use 850 nanometers as the first signal generator. The absorption areas are avoided completely, and the very first one after the absorption area is 1300 nanometers, and then 1310 nanometers were used to make signal generators for the fiber optic cable. And the last one is 1550 nanometers. Here the incidence of scattering is extremely low. So we chose 1550, 1310, 1300, and 850 nanometers as signal generators for fiber optic cables. So manufacturers made signal generators at 750 nanometers and 1300 nanometers. These two used for LED transmitters, which are used with multimode fiber. Now 1310 nanometers and 1550 nanometers are used for laser transmitters, which is used in single mode fiber. Okay, we've come to the end of module number 2 of our fiber optic training. This one was a bit longer than I planned to do, but there were a lot of information that we needed to cover. Next, we'll be going on to module number 3 on our fiber optic training, where we'll be covering multimode and single mode fiber optics. Things are starting to pick up right now. You've been through most of the dry areas, which was necessary in order to get a basic understanding of fiber optics. But things are starting to pick up now, and it should get much more interesting. So if you haven't subscribed as yet, don't forget to hit the subscribe button below so that you'll be alerted when module number 3 is released in the month of August. My name is Trevor Wood, and thank you for watching.